Please, everyone who is here, please take a seat. Okay, let's begin. I'm just going to say a few words before we have a more official welcome. My name is Espen Larsen. I'm a communications advisor at the Environment Agency here in Norway, and I'll be your moderator today. First, if something happens, there are 2 emergency exits. One is down the stair in the back of the room, and when you come down to the 11th floor, there are 2 ways out of there, and they are marked by signs. There's also an emergency exit behind me here. Don't go out on the terrace, and don't use the elevators. Okay? There's a wireless network here. There are actually 2. They're called Zerokonferansen, one of them, and the password for that is konferanse. Just to know, today we are live on the internet. This whole seminar is being webcast, and it will be available later on YouTube. If you feel like sharing your thoughts on Twitter, there are 2 hashtags. There's the hashtag klimapanel, and you can also use the conference hashtag 013. I will encourage those of you who have not contributed with a question to this seminar to put down a question on a piece of paper and put it in one of the boxes in the back of the room before part 3 today. Now we'll have a more proper welcome. Audun Rosland is head of the climate department at the Environment Agency here in Norway. The floor is yours.
Yeah, thank you, and good morning, everyone, and welcome to this this seminar, which also will be followed, as has been said, via webcast. It's great to see so many here. We are actually overwhelmed in that regard. The Environmental Agency, being the focal point of IPCC, it is extremely important for us to communicate new findings, latest findings on the scientific knowledge on climate change. Hence, the purpose of this seminar is to increase the awareness and understanding of the climate science, especially with regard to the latest findings we have got from the Working Group 1 report of the 5th assessment report. So we are then in this seminar focusing on the physical science basis. As I've already said, there are very many here today. I think we are about 200 people, and I think we are representatives for all parts of the society, and that give us a great pleasure. And also, I think we will have a very good seminar in that regard, and good questions, I hope. To make this seminar possible, we have collaborated with CICERO, Bjerknes, and the Norwegian Polarinstitutt. And all these institutions have had authors taking part in the work of this Working Group 1 report of the 5th assessment. And we will, in part 2 of this seminar, hear more from for some of these authors. Øystein Jansen from Bjerknes, Jan Fugleseth, Gunnar Myhre and Cecilie Mauritzen from CICERO, and lastly Jan Gunnar Winther from the Norwegian Polarinstitutt. But they will be properly introduced later on by Espen. But now first, Professor Thomas Stocker, co-chair of Working Group 1. He's professor at the University of Bern in Switzerland, and has a very long reputation as a researcher within several fields. But I will mention the dynamics of climate systems, climate modeling, past and future climate, and ice core analysis. which is, of course, an important part of the understanding of the historic climate changes. Thomas will have 45 to 50 minutes for his speech, and then we will have possibilities to ask questions directly to Thomas. Even though we will come back to a specific part at the later of the day on questions, but you can also raise questions directly to Thomas. So, Professor Stokke, the floor is, and the audience is yours.
Very much. Thank you very much. Good morning, colleagues, friends. I see many lead authors here from Norway who have contributed to our Working Group 1 assessment, which was published about 6 weeks ago in Stockholm at the end of a very long plenary session lasting for 52 hours with very little sleep. So it's a great pleasure here to take the opportunity to explain to you a little bit more in depth what is actually in this report. I do this also on behalf of my colleague co-chair, Jing Dahe from China, but more importantly on behalf of 259 authors who have contributed over the last 4 years to this assessment. They come from 39 countries, and all of them have contributed voluntarily and free of charge to this endeavor. And it's very important that this is being said, many, many times, because there are many misconceptions out there in the public about what IPCC is, who is IPCC, and what do these scientists actually do when they tell us climate is changing. So here are a few impressions from 2 of the 4 lead author meetings that have been carried out over the course of 2.5 years, one in Marrakesh, another one in Hobart. And it's also important for IPCC to go into the different regions of the world and be hosted by the different scientific communities. These lead author meetings are the primary events where the authors sit down, discuss, and actually find consensus on many of the issues that are to be assessed in the course of this work. We have 18% female, and 24% of the colleagues are from developing countries and economies in transition. It is, again, a long-standing effort of IPCC since its foundation 25 years ago to involve actively the developing countries through various mechanisms. I want to explain first a little bit about the process and then go into the scientific results. In 2009, a group of scientists, together with the governments and other stakeholders, have had a conference in Venice to basically outline the scope of this report. In other words, construct a table of contents. What are the issues that the scientists should particularly look at? For example, it was very clear that sea level rise is an important topic that deserved much more attention than in the previous report, and therefore we decided to have an entire chapter on sea level rise. Another topic of great attention was mechanisms of radiative forcing, clouds and aerosols, and their interaction, and we also felt it was time to involve a new community that traditionally stood out a little bit outside from the IPCC process, and that was the cloud physics and meteorology community, who contributed, again, another chapter into our report. So that was this scoping process, which is very important because it's the first point the governments participate and take initial ownership of the assessment process by basically approving the outline with which then the scientists go forward and basically fill this outline and table of content. Once you know what the outline is, you also know the expertise that you require for your report. And out of the almost 1,000 nominations that we received from the governments around the world, we selected 259 authors in various functions. So there are these coordinating lead authors who are responsible for an entire chapter, but then they have available a team of anywhere between 12 and 17 lead authors who basically ensure that the scientific coverage is available to the chapter. In addition to these selected or elected functions, we also put a lot of emphasis to reach out to the wider scientific community and to also invite contributing authors who advised the author team or who provided specific parts where the expertise was underrepresented, for example, in a chapter where these contributing authors would provide a figure or a paragraph or provide the author team with the latest research of which, people may not be aware of papers that are in the submission stage or just about to be published. So this is very important to recognize. It's not just a limited number of scientists, but it's actually a much wider community who contributes to these reports. The reports are produced according to a sophisticated procedure. You can read up. It's boring reading, but it's all on the internet. You can inform yourself how that works. Basically, we are constructing a series of drafts, a zero-order draft, a first-order draft, a second-order draft, and then a final draft. And each of these drafts is sent out to review. And we have, in Working Group 1, received a total of 54,677 review comments. And anybody who has written a scientific paper, I personally, after about 20 review comments, I have enough work to do to revise the paper. Now here you have 54,000, and you can appreciate the amount of work that is behind this assessment, because every single of these review comments has to be responded to. First of all, you have to read them and then respond to and reflect on what you are going to do with this comment and whether that has a consequence for your chapter. I already mentioned we had 14 chapters in our report, ranging from observations, atmosphere, ocean, cryosphere, etc., right into the climate projections. Several chapters that deal with specific topics such as sea level rise, clouds and aerosols, biogeochemical cycles. In total, we have about 1,100,000 words in the report, and we have a new innovative feature for the Working Group 1 contribution, and that is the Atlas of Global and Regional Climate Projection. That is based on the CMIP5 database. These are climate model simulations carried out by 42 models worldwide, summarized in this atlas for 37 regions, all 4 emission scenarios and 3 time horizons. All information eventually electronically available for everybody to use for free. Now, nobody would read from back to back 1,100,000 words, certainly not those people who are in positions to take decisions. That's why it's customary to write summary for policymakers, short, distilled versions, and we have our summary for policymakers, which is online since 27th of September, comprising 14,000 words. Now, 14,000 words is still a lot. It prints on about 25 pages, and that's why early on we said we want to really produce something that, not a coffee table thing, but something that faithfully reflects the very heart of the content of this report. But it is easy to understand, it's quotable, and you get the message. And that is now another important new element in our assessment, that we tried to summarize in just 19 headline statements the essence of the findings of the scientists. These 19 messages print on less than 2 pages. So there is no more excuse for anybody not to know what is in this report. So what I want to do now in the rest of the time is to bring you through some of these headline statements, show you also a little bit more in detail what the scientific basis for these headlines is, and I do that in 3 parts: observation, understanding, and future of climate change. Essentially, that is the flow of the assessment also in the underlying report. We want to respond to the question, what has changed? And one of the first figures in the summary for policymakers is given here. It shows the global mean temperature anomaly relative to the climatological period from 1961 to 1990, since high-quality measurements of sufficiently global coverage are available, and that is since the mid of the 19th century. We depict those in decadal averages, and you see there is natural variability. These temperatures go up and down, but on the long term, on a multi-decadal to century timescale, you actually see a very clear trend. You also recognize that the last 3 decades really stand out, and that has led to one of the first headline statements, which says each of the last 3 decades has been successively warmer at the Earth's surface than any preceding decade since 1850. But we also go further back in time, because you may remember some of the discussions in the public where people say, oh, but in the medieval times it's been much warmer, etc., and therefore sowing doubt on the notion of anthropogenic climate change. We also are clear about that. We say in the Northern Hemisphere, 1983 to 2012 was likely the warmest 30-year period of the last 1,400 years. And you see here also how the scientists convey the fact that this is based on scientific publications, which, there are publications here and there with slightly different messages. But overall, we can make that statement, but we attach to that statement so-called uncertainty language. We say we can make that statement with medium confidence because, for example, that statement is based on paleoclimate information, tree ring analyses, lake sediment analyses, ice cores. All that together indicates to us that, yes, the last 30 years were the warmest, but there are gaps in these reconstructions. There are uncertainties associated with the proxy data, and that is why we flag this to the reader. This is medium confidence. We also say it's likely, chance 2 out of 3, and there is a whole mechanism of using this uncertainty language, which again is explained in a document on the internet. By the way, all working groups, also working group 2 on impacts and adaptation, and working group 3 on mitigation and technological transformation. All 3 working groups use the same uncertainty language. Now, looking now in more details on what has changed in the climate system, we see here the temperature change expressed as a difference over the period from 1901 to 2012 over the Earth's surface. You see the signal is very clear. It's red all over the place in most areas. Some areas even show purple color with a warming over that period of more than 1.5 degrees. But there are also areas where you see blue colors, for example, in the North Atlantic area, indicating that the ocean is extending a convenient service to us. It's actually cooling a little bit by taking up a lot of heat in this area. That's why there is some cooling, but I should say this is not significant based on the significance analysis that the scientists have carried out. And where it is significant, you see these little crosses here in the center of the colored boxes. But there are also areas where the scientists have insufficient information, either due to lacking coverage or time series that are not available in these areas altogether or are too short. And these are the areas where you see the white color. And there are some really large areas where we would like to have some more information. For example, Central Africa, central parts of South America, but also for physical reasons, the Southern Ocean, which is an important part of taking up heat and carbon, but we don't have any long-term records available that we can trust here. Nevertheless, looking at this map and the time series that I've shown you before and many other indicators lead us to reconfirm a statement that has been made already at the fourth assessment report in 2007, and that is warming of the climate system is unequivocal. Although this is the identical statement of 6 years ago, excuse me, it was important for us to repeat this again. In addition, there are also changes evident in the water cycle. You see in these smaller maps, which were actually added in the Stockholm meeting. And Peter Thorne, for example, had really a tough time over 2 days to produce these maps to the level where we were all confident and happy that we could include it in the summary for policymakers. It shows temperature, precipitation changes over the 20th century in the top figure and over the last 50 years of the 20th century in the bottom panel. And you already see indications that there are latitude bands where there has been an increase in precipitation that would be indicated with the blue colors, and areas where there has been a reduction in precipitation. But you also realize that the situation has much less coverage than for the variable temperature, so precipitation measurements usually pose a serious limitation to the scientists when they want to assess these observations. I show here another time series of significant changes in the climate system, and this is the time series of carbon dioxide concentrations as reconstructed using polar ice cores. We've done that in our institute at the University of Bern. We took in collaboration with many European countries in the course of a European project an ice core from Antarctica, and this ice core contains air, and this air allows us to reconstruct back 800,000 years the greenhouse gas concentrations of the atmosphere. I only show you here carbon dioxide, which is the most important greenhouse gas after water vapor. And you see there are natural variations of this concentration in the atmosphere, but if you compare that to the direct observations in the atmosphere that we have available in the past 60 years, you see that we're way outside of the natural band of variation, with an increase in concentration over pre-industrial of over 40% by now. And you also see this curve points up almost vertically on this very long time series. We have a rise in carbon dioxide that is at least 100 times faster now than ever in the past 22,000 years. So we're really outside of anything that is normal. That's why we say the atmospheric concentration of carbon dioxide and two other greenhouse gases that can be reconstructed the same way have increased to levels unprecedented in at least the last 800,000 years. Here is another important graph out of now the technical summary. That is another document that the scientists have prepared, a more extended summary of the science. And you see here the cumulative melting of ice from the cryosphere, that is from the glaciers, from Greenland and Antarctica. And again, these curves also point upwards with about 4,000 gigatons at the year 2008 lost through glaciers, about 2,000 or 1,000 gigatons lost by Greenland and Antarctica cumulative. Now, gigatons are hard to comprehend. That's why we also put it in relation with sea level rise. If you melt that water, that leads to sea level rise, and you see that the glaciers have contributed over that time by about 14 millimeters of sea level rise, and the two ice sheets together, again, about 14 millimeters of sea ice. We also quantify that now. For the first time, we have a good coverage, and thanks to satellite measurements, also a good estimate of how much mass has been lost in Greenland and Antarctica. Although the uncertainties are still relatively large, 60%, 50%, and so forth, this allows us for the first time to close the budget of sea level change for the observational period. In other words, we have all the components together measured independently, the expansion of ocean water contributing to sea level rise, glaciers, Antarctica, Greenland, and all together within the uncertainty matches up to what we observe independently as the rise in sea level. This is a major achievement of the last 6 years. This also is a major achievement because we have now better measurements of the salinity content of the ocean, in particular at the surface. And here you see an extremely fascinating conclusion indirectly by looking at the changes in salinity over the world ocean that indicates that there are large-scale changes of the water cycle. In other words, changes in the precipitation and evaporation patterns. So I just draw your attention here to the second panel, which shows this map in perspective with the red areas where you have mean evaporation and the blue areas where you have a dominant precipitation. So you see the tropics, the subtropics, and then the higher latitudes with more precipitation. And in the third panel, you see the trend in surface salinity, and you see that this surface salinity increases in those areas where you have these already conditions of excess evaporation. So where it's evaporating and where you have a shortage of precipitation, we observe in the ocean even a greater tendency of salinity to increase, which indicates that latitudes where it is wet become wetter, latitudes where it is dry become drier. Overall, we say regional trends in ocean salinity provide indirect evidence that evaporation and precipitation over the oceans have changed. This is an important statement because routinely we don't go and measure evaporation and precipitation over the ocean. So you do it indirectly, and the data now permit this medium confidence statement. There are also other things that change in the ocean. For example, the ocean heat content, an important quantity, as you see in a minute. This is again possible thanks to massive investments in autonomous measurement devices that have been deployed in many parts of the ocean that now permit us to track temperature changes, from which then the change in the energy content of the upper ocean, that is the upper 700 meters of the ocean, can be calculated and estimated. And you see the signal here is very clear. Since about 1980, the uncertainties have been reduced massively, the data have increased in quality, and the tendency is very clear here. We conclude it is virtually certain that the upper ocean warmed from 1971 to 2010, and it is likely that the ocean warmed between 700 meters and 2,000 meters over the longer period since the late 50s. This is an important statement because the heat is not only limited to the top 700 meters, but ultimately it will concern and cover the entire volume of the world ocean. And that leads us to a second achievement, new achievement in AR5, in which we can close the energy budget. And for a report that has in its title the physical science basis, energy change is arguably the most important quantity when it comes to identifying climate change. You see here a time series since 1970 of the energy change, and it's stacked here with the sky blue indicating the energy change in the upper ocean, dark blue the deep ocean, white in the ice because you have to melt the ice. That costs some energy, but it's a small fraction. The warming up of the land surface also requires energy. That's the brown fraction. And the very tiny bottom fraction here in purple, that is the energy that you require to heat up the atmosphere. And isn't it paradoxical almost that whenever we talk about global change, we are fixated on temperature changes in the atmosphere. And yet from a physical point of view, it's really negligible if you look at the amount of energy that is stored in addition to what we have in the natural system. It almost exclusively resides in the ocean and is a powerful indicator of the profound changes that we have imparted on this system. We say ocean warming dominates the increase in energy stored in the climate system, accounting for more than 90% of the energy accumulated between 1971 and 2010. And we make that statement with high confidence. Let me now go to the next section, understanding. Now, we have observed what has changed. In fact, in every compartment, in every component of the climate system, the atmosphere, the ocean, the cryosphere, the biosphere. Now we ask the question, why has it changed? And here I show a rather complex figure, which also many people have worked many hours, around the clock almost, to come up with this figure. And even the co-chair now finally understands this figure. It's a great figure that tells you what is really driving this system. And we do this through the concept of radiative forcing, which says for the different components in the atmosphere, how much watts per square meter does a constituent cause the radiative or the energy flux to change. And we reference that since pre-industrial, since 1750. And the figure is constructed such that you see these changes in watts per square meters as these horizontal bars. Pointing to the right means positive and therefore warming. Pointing to the left means negative and therefore cooling. And you see many, many components in the atmosphere that we order according to the emitted component. So, for example, emissions of carbon dioxide result in changes in concentration in carbon dioxide, and that amounts to a forcing of about 1.68 watts per square meter since 1750. The next important one is methane. An emission of methane leads, first of all, to increases in concentration of methane, but then there's a series of other molecules which have cause additional greenhouse forcing, and these are created through chemical processes, such as additional CO2 a little bit, stratospheric water vapor, and ozone, and together, caused by the emission of methane, cause a forcing of about 1 watts per square meter. And so you can go through all the components, can add them up. You also realize that there are constituents that cause a cooling. The aerosols cause a cooling. And you can then add up all these bars, and you can appreciate that constructing such a figure out of the scientific literature and then attaching to each of these forcing bars an estimate and an assessment of uncertainties. This is a really large effort that is fundamental to every assessment. We can also show a an indication of the time evolution of this forcing. Since the 1950s, you see that forcing has really increased. And as such, this is the basis of a fundamental understanding as to the reasons of the changes that we have observed. The largest radiative forcing is provided clearly by carbon dioxide, and that is one of the reasons why we are so focused on carbon dioxide, primarily also when it comes to future climate change. I've shown this already, and we say the total radiative forcing is positive. We are adding energy to the system. We've already observed that in the ocean, and this has led to an uptake of energy. The largest contribution is caused by the increase in CO2 concentrations. Now, the increase in CO2 concentrations creates and triggers some feedbacks in the climate system. It's not only the carbon dioxide that is responsible for the climate change, but primarily the carbon dioxide acts through feedback mechanisms, most importantly associated with water vapor. Water vapor increases in a warming atmosphere and is able to double the effect of carbon dioxide changes in the atmosphere. You see here a summary of these different feedback mechanisms as they are estimated from model simulations. Fundamental feedback that keeps our climate system stable. It's the so-called Planck feedback, which is negative. It means whenever you impart a change to the system, it tries to come back to the original equilibrium. But there are also positive effects, and we are more concerned about those. Reinforcing effect, for example, with the water vapor up here, or the lapse rate and the water vapor combined, or the cloud feedback, which, as you see, has a large uncertainty. Some models even have a negative cloud feedback, but I think we now have come to the conclusion that overall the cloud feedback is actually positive, as is, in a smaller scale, also the albedo feedback. Overall, the sum is a positive feedback on the order of about 1.5 to 2 watts per square meter per Kelvin, and you can now put that into relation of climate sensitivity. This number here directly influences or determines the climate sensitivity of the system. Now I'm watching my watch a little bit. This is another topic that has concerned us actually in the second half of our assessment, because only then it became evident that there is such a wide interest, not only of the public but also of the science, what really happened in the climate system in the last 15 years, during which we see a temperature trend that is significantly smaller than the temperature trend determined over the last 100 years. Some people talk about a warming pause or a hiatus. The scientists would like to know what is the reason for this. Now, you see here the temperature trend as determined from observations in red, given in degrees Celsius per decade, and for different time windows. That's sort of the publicly defined window of interest. It starts in 1998, which, by the way, was a very strong El Nino event. And you have here longer windows, and the longest window, 1951 to 2012. And we compare that with the trends that the climate models actually simulate, given in the gray distribution. And you see, basically, this graph has created a lot of media attention and skeptics' attention, in that they say, look, what you observe is basically at the lower end of the models. Now, as a scientist, you have to say it's not completely inconsistent with the models, but it's true. The majority of the models, as you see here, are not able to simulate the low trends of temperature precisely in that 12-year or 15-year window from 1998 to 2012. Now, this opens up a broader scientific question: to what extent models are capable to predict decadal changes in the climate system. In other words, to predict 10 years ahead of time the occurrence of a strong El Nino in 1998, and then a series of volcanic eruptions from 2005 onwards. Now, we've looked at that very carefully in a more general sense in a dedicated chapter in our assessment, and we have identified many reasons why this is an extremely difficult task. One of the reasons is, first of all, volcanic eruptions cannot be predicted, so that you can tick off. El Niño, you simply don't have sufficient information from the climate system to be able to predict that phenomenon longer over times, lead times longer than 6 or 7 months. So it's not a surprise that if you put the models to such a test, that there is not a great agreement, because the question is actually posed in a wrong way. If you, however, then increase the time window to about 60 years or even a shorter window here, then the situation changes. The observations become much narrower, and you see a very good agreement of the 60-year trend with the observations. This also brings me to the question, was the forcing appropriate that these models were using? I've already mentioned the volcanoes, but there is also other forcing elements that are relevant for this 15-year period. Remember, the model simulations start with a scenario calculation already in the year 2006. So for about half of this time, we have made assumptions based on scenarios rather than on observations. And that's another limitation of these models. The forcing, again, is very appropriate for the large time window. That's why we also get so good agreement. But for the smaller window here, you see some models underestimate the forcing. Other models have a larger forcing that they were using. And therefore, there is still a lot of questions around this, not the least, where has the heat gone? And that question has still not been resolved. There are suggestions that the heat is actually stored in the deep ocean, only that this is very hard to detect, if not impossible. And others have suggested that the tropical Pacific may play a very major role in that. Irrespective of that, over the last 60 years, we have a warming of 0.6 to 0.7 degrees Celsius. That is a fact. And we now can associate that warming and attribute it to the drivers that I have explained. Now, there are the greenhouse gases that constitute a warming, and the warming is actually larger than what we observe, and therefore there must also be cooling effects in the atmosphere, and they are afforded by the aerosols, as you see here in the bars. If you add the yellow bar and the green bar, you get the anthropogenic forcing, which constitutes just about the temperature that we observe. Solar volcanic variations, but also internal variability, they are unable to provide enough forcing to explain the 0.6 to 0.7 degrees Celsius. And that is why we say it is extremely likely that human influence has been the dominant cause of the observed warming since the mid-20th century. Now, there are many other indicators where we can make that detection and attribution statement, like sea level rise, Arctic sea ice cover reduction, melting of Greenland, temperature changes in all the regions of the world except for Antarctica, changes in the ocean heat content. And that all together led us to a very simple, probably the simplest statement in our assessment, which says the human influence on the climate system is clear. And now everybody can say that. That's a quotable sentence in the media, but remember, this is a sentence that, first of all, the 259 scientists have agreed to, and then, more importantly, the 195 governments that constitute IPCC have actually agreed to that. They are in consensus with this statement. Let me now come to the last part, which is concerned with the question, how will it change? The first figure is always this one, which shows a time series of the model simulations, first over the historical period from the mid-20th century to the year 2005, which is given in gray, and then, just for illustration, a business-as-usual scenario given in red, and a emission reduction scenario given in blue. We also indicate uncertainties shown in the bands and the multi-model mean over 39 or 32 respectively of these climate models given in the curve here. What we show is the global mean temperature change relative to 1986 to 2005, and you see these scenarios are very different. The business as usual scenario shows a warming by the end of the 21st century of just about over 4 degrees Celsius, whereas the other scenario shows stabilization at a warming of about 1 degree Celsius relative to that time period. You should add about 0.6 degrees Celsius if you want to explore the temperature change relative to pre-industrial, which is the policy-relevant time period, and therefore we cast our simple statement using that number. We say global surface temperature change for the end of the 21st century is likely to exceed 1.5 degrees Celsius relative to an approximation of pre-industrial for all scenarios, except that one policy intervention massive emission reduction scenario, which is called RCP 2.6, this blue scenario. So we do have a chance, but only one out of the 4 scenarios that the scientists have used in their calculations actually manages to stay below the 1.5 degrees Celsius. There are many variables that you can now plot and quantify in these climate models. I've just brought one here, the Arctic sea ice cover evolution over the 21st century for the 2 scenarios. And you see that the blue scenario would actually stabilize Arctic sea ice cover at the end of the summer in September at a low number, much lower than today, but still there is some ice left in September, whereas the business as usual scenario shows indeed that we are approaching nearly ice-free conditions before the mid-century. And that is the associated statement that the scientists have made and has been approved in Stockholm. A nearly ice-free Arctic Ocean in September before the mid-century is likely for this high emission scenario. And we make this statement cautiously, with medium confidence, because as you see, there are only a few of the 40 climate models that are capable to provide a credible projection of Arctic sea ice cover in September. Another quantity, just by way of example, because climate change is not only about average values and annual means, but a lot of it, and the biggest challenges to us, is actually changes in statistics of extreme events, as was already dealt with in IPCC with a special report that was published in 2011. Here I show from these simulations the occurrence of warm days. So what is today the 10% warmest days becomes more frequent in all scenarios, but most frequent it becomes obviously in the business as usual scenario. We say it is very likely that heat waves will occur with higher frequency and duration, but still we will have some cold winter extremes. They will continue to occur, but obviously their frequency will be much lower. What is important to know is the fact that the statistics of extreme events in the tails of the distribution, they change by factors, and you can read it off here for the warm days. In the course of the 21st century, it changes by a factor of 6 times more frequent, in some regions even up to 10 times more frequent. So these are the first things that people realize when they look at the climate record and the record of extreme events. Sea level rise, another important quantity for many countries. Here we can give a comprehensive assessment of the future sea level rise in the 21st century for the first time, including all the components. And you see that it is likely that for the business as usual scenario, we have sea level rise of between 26 to 55 centimeters and up to a meter in the likely range for the other scenario. Let me now come to the last figure in the summary for policymakers, arguably the most policy relevant figure because it changes the paradigm of how you look at the climate system in the future and how you look at the primary driver of the changes ahead. What you see here is a new concept that says that all carbon dioxide emissions together since pre-industrial actually determine the warming. So we have a limited amount of carbon associated with a particular temperature. And we illustrate this by showing this figure here. On the horizontal, you plot the cumulative anthropogenic emissions since 1870 and the warming that is simulated by these same models relative to that same period. And I just now animate this graph by just saying cumulative emissions largely determine global mean surface warming. And you see that illustrated now as these simulations are carried forward with the 4 scenarios given in the different colors through the 21st century. And we are approaching now the year 2100. You see that in this graphics, the 4 emission scenario actually are distinguished not by their path. They are remarkably moving in this graph on the same path, but it's the time point where they stop or the point at the cumulative emissions where they stop. For the low emission scenario, 2100 stops here at this emission, cumulative emission, and stops just under 2 degrees warming, whereas the business as usual scenario goes up all the way to cumulative emissions over 2,000 gigatons in total, creating a warming of over 4.6 degrees Celsius. So if you now are a policymaker, you have an instrument. First of all, you have to also consider the uncertainties. They are large, but they do not change the major message, and that is that cumulative emissions determine the warming. In other words, there is a linear relationship between these two quantities. And we investigate and find that to limit CO2 warming, induced warming to less than 2 degrees Celsius, the cumulative emissions must be limited to 1,000 gigatons. That's the trillion ton many people are talking about. And you can read that off from the graph here, 2 degrees, somewhere in the middle of this uncertainty range, and you go down with your arrow and you land at 1,000 gigatons. That's the total amount available. Now, if you then say, but there are also other drivers, other greenhouse gases that we are emitting through agricultural processes such as methane and N2O, this allowable amount is actually 20% smaller, only 800 gigatons, and you see that if you place yourself here at 2 degrees, go only to the scenarios, and then you see that you have even less available to burn and emit. Just as a reminder, as of today, we have emitted a little bit more than half of that budget that is available to us. So the policy relevant question now is, how do you divide up the remaining pie, provided you have actually decided that you want to limit climate change? So that's why we say in our summary for policymakers, limiting climate change will require substantial and sustained reduction of greenhouse gases. It means that there is only a finite pie that you can eat from now on, the pie of these greenhouse gas emissions. Let me close with, again, showing you what it means to decide for a low emission scenario or a high emission scenario by showing here the temperature changes as a map for the intervention scenario 2.6 and for the other scenario here a totally different world, more than 4.5 degrees warmer over the continents, more than 4 to 5 degrees warmer in the high latitudes, warming in excess of 8 to 9 degrees, with massive changes that are ahead of us if we decide for this scenario, whereas the warming is limited but also enhanced in the high latitudes. So 2 degrees limiting does not mean 2 degrees everywhere. In Switzerland, we will have about 3.5 degrees. In Norway, you will also have larger temperatures, and in the Arctic, we would experience, under that scenario, temperatures of 4 or 5 degrees of warming. Now, if you look at these two graphs, these two maps, you realize we do have a choice, because it's our decision which of these scenarios, which of these pathways we will develop in the future. And finally, it's not only temperature when we talk about global climate change. It's also the primary resource to humankind and ecosystems, which is water. And you see here the changes projected through these models for precipitation by the end of the 21st century. Almost all areas are covered with this hash pattern here, which indicates that we cannot distinguish that from the natural variations of precipitation throughout the 21st century. So limited change, but the sign of the change is already visible. This is very much different for the high emission scenario, business as usual, where we see intensive colors of blue, more precipitation, but also brown colors, less precipitation. And it's again the familiar pattern of the wet latitudes here in the tropics and the high latitudes. They become wetter, and the dry latitudes, who are challenged already today through water shortage, will receive even less water. We have a choice again, and I thank you very much for your attention. All the details are on this website. Thank you very much.